I was in a Zoom meeting this morning, camera off, just listening, and I had this weird moment. I stopped listening to what people were saying and started listening to how they were doing it.
The meta listening experience.
Exactly. I mean, think about it for a second. You have a thought, just a spark in your brain that says, I disagree with that marketing strategy. And instantly, without typing a single line of code, your brain just converts that spark into grammar, syntax, tone, sound waves. You don't pause to look up a conjugation table. You just speak.
It is arguably the most complex thing we do as humans, and we do it while, chewing gum.
But then I look at my GPS or even some of the older chat bots, and it's like watching a robot try to walk on ice. It's clumsy, it's just weird. And that is exactly what we're unpacking today. We are doing a deep dive into natural language generation, or NLG.
Which is a huge topic.
It is huge. And to keep us grounded, we're looking at a serious heavyweight of a text. We're breaking down Chapter 32 of Principles and Architectures of Natural Language Generation.
By John Bateman and Michael Zock. Yeah, this is a great choice because it really steps back from the current hype cycle, the LLMs, the chatbots, and it looks at the fundamental architecture.
Right.
It asks a really basic question. How do you bridge that gap? How do you take non-linguistic data zeros and ones, a database, a spreadsheet, and turn it into a fluent or funny or persuasive paragraph?
The authors define NLG as a knowledge-intensive problem.
Which is a very fancy way of saying it's hard.
It's very hard.
The core idea is mapping information to form to fulfill a goal. But Bateman and Zock, they make this comparison right at the start that I think is just brilliant. They separate simple systems from complex ones to explain why language is such a nightmare to engineer.
This is the gravity comparison, isn't it?
Right. So think about a glass falling off a table. Gravity pulls, the glass hits the floor, the glass breaks.
A clear causal chain.
It's a linear causal chain, a hierarchy of events. We get the physics. If you drop the glass, it will fall every single time.
Gravity is reliable, doesn't have an opinion on what you're wearing or the time of day.
Exactly. But language, the authors say language is not a hierarchy. It's heterarchically organized.
Okay, let's unpack that word, heterarchy. Sounds like something from a biology textbook.
It basically means a system where there's no single boss. In a hierarchy, the boss tells the manager who tells the worker, top down. In a heterarchy, everything influences everything else at the same time. The authors compare it to biology or society or politics.
Politics, that seems like a bit of a stretch for computer code.
It's actually perfect. Think about a politician giving a speech. They have a goal, get elected. But every single choice they make constrains every other choice they can make later.
How so?
Well, if they pick a very formal tone at the start of a sentence, they can't suddenly switch to slang 5 seconds later. It breaks the spell. If they choose a specific word to describe a policy, it ripples out. It limits how they can talk about the consequences of that policy 3 paragraphs later.
So you can't just swap words in and out like they're Lego bricks.
Not at all. The text says that speaking well is like being a skilled politician. You have to make the right choice at the right moment, and the consequences of a bad choice are far-reaching and unpredictable. You might be grammatically correct, but you could still confuse your listener or insult them or just sound weird.
And that leads us right to what the authors call the problem of choice. I feel like this is the heart of it all. The reason it's so hard to teach computers to write isn't that they can't write, it's that they have way too many options.
Infinite options. And unlike a politician, the computer doesn't have intuition. It needs rules.
The text actually has this really specific case study on this that I found fascinating. It's the population leaving example. I think we should walk through this because it really shows the gears turning.
Let's do it. It's a classic NLG problem.
Okay, so imagine the computer has this tiny little database. It knows 3 concepts: leave, population, and place. That's it. That's the raw data.
The semantic input, leave, population, place.
Right. Now, the computer has to figure out how to say that in English. So it generates option A. The place was abandoned by them.
Okay, so critique that. Is it English?
I mean, technically, yes. Subject, verb, object, but it's awful. The place is so vague, and by them, who is them? It sounds like a riddle.
Right. It's grammatically perfect, but communicatively, it's terrible. The text would call that sentence infelicitous.
Infelicitous. I love that word. It sounds so polite. Excuse me, sir. Your sentence is infelicitous.
It's the proper linguistic way of saying technically correct, but socially or contextually just Awkward.
Okay, so let's try option B. The computer tries again. The city was abandoned by its population.
Now, this is better. But the authors actually critique this one, too, and this is where you get into the really deep details.
See, I thought this one was fine. What's wrong with it?
It's about markedness and something called the given-new distinction. In a story, if we're talking about a population leaving, we probably already know the city exists, right?
Yeah.
We've likely mentioned it in the previous sentence. So if you say the city, again, using the full noun, you're marking it as new information. You're signaling to the listener, hey, pay attention, I am introducing a city.
But the listener is thinking, I know about the city. Why are you reintroducing it? It creates this tiny cognitive stumble.
Exactly. It's like when you introduce your friend Bob to someone who has already met Bob. This is Bob, and everyone's just like, we know! It's weird.
So what's the winner? What's the felicitous choice here?
Variant C. It was abandoned by its population.
It.
Just it. Using the pronoun flows better because it respects that given new distribution. You use the small, low-content word it for the thing we already know about.
And you save the big words for the new information.
Exactly.
So the big takeaway here is you can follow every rule in the grammar book and still fail at communication if you don't understand the context.
Precisely. And that is why this is so hard. The computer has to know what to say and also how it fits into the flow.
So how do they even build these systems? The text lays out a kind of blueprint for NLG. It seems like for a long time there was a pretty standard pipeline structure.
There was. And you can think of it like a factory assembly line. It generally has 3 big stages. You start with macro planning, then you go to micro planning, and you finish with realization.
Okay, let's break those down. Macro planning is the what, right? The big picture.
Yes. Content determination. What are we actually going to talk about? The text uses a weather report as an example, which is perfect.
So imagine you have a weather database. It's got humidity, pressure, wind speed, temperature for every minute of the day.
Thousands of data points. If the computer just read that database to you, you'd drive your car off the road.
1:00 p.m., 70 degrees. 1:01 p.m., 69.8 degrees.
Right. So the macro planner has to do 2 things. First, filtering. It deletes the boring stuff. But the second thing is crucial, interpretation. The test points out that if the temperature numbers go 70, 60, 50, the computer shouldn't just list them. It needs to look at that curve and generate a concept.
The concept of a drop or a decrease.
Exactly. The data is numbers. The macro planner turns it into the idea of cooling down.
Okay, so we have our concepts. We know what to say. But how do we organize them? The text mentions 2 main ways computers do this: schemata and rhetorical structure theory.
These are kind of the 2 rival schools of thought. Schemata, that comes from a researcher named McCune. It's basically using templates.
Like a fill in the blank.
A sophisticated one, but yeah. Think about a dictionary definition. They always follow a pattern, right? Identify the object, list its parts, give an example. It's a recipe.
A toaster is an appliance. It has slots and coils. It is used to toast bread.
Perfect. That's the identification schema. It's reliable, it's fast, but it is very rigid. You can't write a novel with the schema. It's just too robotic.
So if you want to be more persuasive, you use the other one, rhetorical structure theory.
RST, yeah. This is much more flexible. Instead of a flat template, RST is like building a tree of logic. You break text down into relationships. You have a nucleus, that's the main point, and satellites, the supporting info.
Give me an example of that. Nucleus and satellite.
Okay, if I say, I'm not going outside because it's raining.
Yeah.
The nucleus, the core message is, I'm not going outside.
And because it's raining is the satellite.
Right. It supports the nucleus by offering a cause. Computers use RST to build these massive, complex trees of relationships to make sure every sentence logically follows the last one.
And this connects to one of my favorite parts of the chapter, which is where they bring in Ed.
Ah, yes. Ed and his trip to New York.
I really did not expect a travel itinerary in a coding textbook, but it made the logic click for me.
So the authors are explaining how AI plans a text. And they use the analogy of a travel plan. The computer has a goal state. Ed is in New York.
But right now, Ed is at home.
So the computer has to work backward.
Backward?
Yeah, it's called backward chaining. It asks, what is the prerequisite for being in New York? Well, Ed needs to take a trip. Okay, what's the prerequisite for taking a trip? He needs to be on board. What do you need for that? You need a ticket.
It's a dependency chain. You can't do step C without first doing step B.
Exactly. And the text argues that writing a document works the exact same way.
How does that apply to writing something like a help manual?
Well, suppose the goal isn't Ed in New York, but user understands how to save a file. The computer breaks it down. Goal. Save file requires action. Choose menu. That requires action. Click Save. These are called plan operators. The computer is literally planning the text like a logistics AI plans a shipping route.
That is fascinating. So it's not just writing, it's problem solving. It's saying, my problem is the user is ignorant of X, and my solution is to apply these sentences to fix their state.
Ideally, yes. This is the whole symbolic AI approach. It's logical, it's structured, but this brings us to the danger zone, what the text calls the danger of the pipeline.
This sounds dramatic.
It is, for a software engineer. We talked about the assembly line. Macro planning first, then micro planning. The problem is, in a traditional pipeline, that's a one-way street. You decide what to say, then you decide how to say it.
And you can't go back.
You can't. And the text introduces this concept from a researcher named Meteor called the generation gap.
Which is not about boomers and Gen Z.
No, it's a deadlock. It happens when you make a conceptual choice early on that, well, it paints you into a linguistic corner later. They use the fisherman example here, which is subtle but brilliant.
Okay, let's break that down because I think everyone has felt this when they're writing, even if they aren't a computer.
So suppose the computer wants to express two concepts. A man who catches fish for a job and moved fast on the ground.
Okay, so macro planning says, map concept 1 to the word fisherman. Map concept 2 to the word rushed.
The fisherman rushed. Simple, efficient. But here's the trap. Suppose later in the paragraph the computer realizes, based on that flow we talked about, that the sentence needs to be in the passive voice to fit the rhythm.
Passive voice, so the fisherman was rushed.
Think about that. The fisherman was rushed. Does that mean he moved fast?
No, for something he was rushed to the hospital. Or a sorority or something.
Exactly. You've changed the meaning. The verb rush, effectively, cannot be passive in this context, but the computer's stuck. It already committed to the word rush back in the macro stage. Now it's at the micro stage trying to apply grammar rules, and it hits a wall.
It's like building a house and realizing on the 3rd floor that you put the stairs in the wrong place, but you've already poured the foundation.
That is a perfect analogy. And because the pipeline is one way, the system can't just say, oops, let me go back and pick a different verb. It just crashes or it outputs garbage.
This generation gap, this mismatch between what we want to say and what the language lets us say, that seems like a deal breaker.
It was. It was the massive headache of NLG in the 90s.
So how did they fix it? Because clearly my phone doesn't crash when it suggests text. This leads us to the final section, the statistical revolution.
Yes, this is the big shift. For a long time, we tried to hand code every single rule. If noun is singular, add es to verb. But around the 90s, researchers like Knight and Hatzofasiloglu basically said, stop trying to be so smart.
Stop trying to be smart. I like that advice.
They moved from a symbolic, rule-based approach to a statistical, probabilistic one. Their solution to the pipeline problem was overgeneration.
Overgeneration, explain that.
Instead of trying to find the one perfect rule to get from fisherman to a sentence, they said, let's just generate 50 variations, let's make a mess. They create what's called the word lattice.
So they generate the bad sentences on purpose.
Everything. The garbage, the almost good, the perfect. And then they use a statistical language model to act as a judge.
The preposition example in the text was what made this click for me. Prepositions in English are just a nightmare.
Totally illogical. Why do we say at 5 o'clock, but on Monday and in February?
I'll see you Monday. Yeah, I'll see you on 5-0.
It just sounds wrong to us, but explaining why in code is incredibly complex. You need rules for days of the week, holidays, specific times, duration. It's a mess.
So in the statistical way, the computer doesn't know the rules.
Not really. It just generates small. At Monday, in Monday, on Monday. And then it looks at a massive database of human textbooks, websites, articles, and it asks which of these strings appears most often.
And the model says, well, humans say on Monday 99% of the time.
So the computer picks that one.
It doesn't know why it's right. It just knows it's probable.
Exactly. It bypasses the need for deep linguistic understanding. It solves the generation gap by brute force. If the fisherman was rushed, has a low probability score, the model will just pick a different variation that scores higher.
And this essentially is the grandfather of the deep learning era that we're in now.
It is. The text touches on this near the end. Neural networks, what we use now for ChatGPT and Gemini, are the ultimate statistical machines. They are incredible at being fluent. They sound so human because they've basically read everything humans have ever written.
But the text adds a little caution here, which I think is really important. It says these systems struggle with coherence and truth.
That is the trade-off. Think back to Ed going to New York. That old system was clunky, sure, hard to code. But it had a plan. It knew that ticket was a prerequisite for boarding. It understood the logic of the world.
It had a communicative goal.
Right, a neural net. It's just predicting the next most likely word. It's like an incredibly charming improviser on stage who speaks perfectly, uses amazing vocabulary, but has absolutely no idea what the plot of the play is.
Because it skipped the macro planning stage?
It skipped the explicit logical planning. It can simulate it, sure, but over long texts, these models can lose the thread because they don't have that hard-coded Ed must get to New York logic underneath. They might send Ed to Chicago just because Chicago statistically appears near New York in sentences.
So we've gone from these rigid logical systems that knew the truth but couldn't speak well to these probabilistic smooth talkers that speak beautifully but might be hallucinating.
And the authors suggest that the future, and we are seeing this research now, is probably a hybrid. We need the fluency of the stats, but we also need to inject the structure and the goal setting of the old architectures back in. We need the politician's smooth voice, but also the logistician's map.
So let's bring this all back together. We started with raw data that leave. Population, place. We saw how difficult it is just to choose the right sentence without being infelicitous.
We looked at the pipeline planning content, choosing words, checking grammar, and we saw how you can get trapped in that generation gap.
And finally, we saw how statistics kind of saved the day by letting the computer guess and check against what humans actually say.
It really makes you appreciate your own brain. I mean, we do macro planning, micro planning, and realization in milliseconds.
While drinking coffee and driving a car.
And we usually manage to avoid the generation gap. Or if we hit it, we self-correct instantly. You know when you say, what I'm trying to say is, that's you backtracking in your own pipeline. You realized your micro-planning failed, so you went back to macro-planning to grab a new concept.
I'm going to be thinking about that all day now. Every time I stumble over a word, I'm just debugging my own code.
Basically.
There's one last thing I want to leave you with. We talked about Ed and the why. In those old systems, if the computer picked the word ticket, we knew exactly why. It was a precondition for get on.
Right. It was explainable AI. We could look at the code and see the logic trail.
But in these modern statistical systems, if you ask, why did you choose the word on instead of at? The answer is just. Because the math said 99%.
It's a black box.
And as we start using NLG for more critical things, medical advice, legal summaries, news reports, how much does it matter that we don't know why the computer chose the words it did? Does fluency matter more than the architecture of truth?
That is the question of the decade. And honestly, looking back at Bateman and Zock, you realize we haven't solved the fundamental problem. We've just found a very statistically convincing way to hide the complexity.
Something to think about the next time your phone suggests the next word in your text. Thanks for listening to The Deep Dive.
See you next time.